Okay, so welcome to the first sort of lecture. The few of you who missed this in person, this is sort of the alternative since I didn't have Zoom this morning. So to start off, we're going to talk about just sort of plotting things in 3 dimensions, so 3D coordinates, stuff like that. But before we jump into that, whenever you sort of learn a new mathematical concept, I think it's important to sort of contrast it with something you know already. So I'm going to recall 2D coordinates. So this part, first no more than 10 minutes, should be 98% review. So first, a piece of notation that we're going to introduce, mostly because we're now going to sort of start switching between 2 dimensions and 3 dimensions. So R2, sort of written like this, is going to denote the XY plane. And to start off with a pretty basic example, let's go ahead and plot the following points. So let's say 5, 1, 1, negative 2, and negative 3, 1 in R2. Right. So to distinguish them, I'll associate each of them a different color. Right, so for 5, 1, which I'll do in this green, I go 5 over on the x-axis. I guess I should label my axes. And up 1. So boop, boop, boop. Something like this. 1, negative 2. Get that. And negative 3. So 3 back and 1 up. Okay. So yeah, so remember, this is how we plot things in sort of a 3-dimensional space. And sort of the other thing I want to recall is the distance formula in 2-dimensional space. So I don't just want to recall the distance formula, I want to remind you why it works. So if we look at the distance from x1, y1 to x2, y2, so there's my point x1, y1, there's my point x2, y2, and then what I'm going to do is actually draw a right triangle. That's my distance that I'm after. So if I draw this right triangle, then this length, right, this is the difference in sort of how we move in the x direction. So this is going to be the absolute value of the difference. That is what that length is. And this is going to be the absolute value of the difference of my y coordinates, so y2 minus y1. Or you could do y1 minus y2. And so then, by Pythagorean theorem, I have that my distance squared is equal to x2 minus x1 absolute value squared, which is the same as just squaring it, and then the same for y2 minus y1. And if I just go ahead and solve for distance, I get the square root of the difference of x2 minus x1 plus y2 minus y1. Okay. So we got that, we got the distance formula. Do remember how it works. It's the Pythagorean theorem. That's what we're doing there. Okay, one last example I want to give in 2D before we make the jump. So this is something that I'm guessing you guys were taught in Calc 2, but it's something that I think a lot of people sort of learn and then forget right away. So x squared plus 2x plus y squared equals 3 describes a circle. Or wait, I'm sorry, I jumped to the wrong one. So we got to start with the easy one first. What is its center and radius? And it's also a good idea while we look at this to sort of remember why the formula for the circle is what it is. So right, so if we compare this to this, then what this says is solutions are points which are a distance of 4, right, because that's the square root of 16, from, and then just comparing, well, I'm subtracting 1, so that's got to be a 1, and then I'm adding 2, which means I must have subtracted -2. So my center is got to be 1, -2, and my radius is 4. Okay, so now slightly more complicated version of this. X squared plus 2x plus y squared equals 3 describes a circle. This one's not as free. Find its center and radius. So what we want to do here is complete the square. So we have an x squared and we have a plus 2x. So what we want to do is sort of absorb this 2x into just one thing squared. So we complete the square. And remember, to figure out what you add, you just take this number, divide it by 2, and square it. So 2 over 2 squared. And I guess just to point out what I mean, I'm just going to make these 2's the same because I just want to make it clear this 2 is coming from here and that other 2 is what we're dividing by. 2 over 2 is 1, so I'll just add 1 to this side as well. So I get x squared plus y squared equals 4. So my center is going to be -1, 0, and my radius is going to be the square root of 4, which is 2. All right, so moving on. So 3D coordinate systems. So we're actually going to deal with a couple different three-dimensional coordinate systems, but we're going to sort of start for at least, the first third of the class, just talking about sort of the normal Euclidean coordinates. Which we'll just call the XYZ plane. And we might denote it as R3 to again sort of distinguish it. What I mean by sort of going into different coordinate systems, you may remember sort of polar coordinates, another way of giving coordinates to the plane. We're going to go through a couple others for three-dimensional space as well. Okay. So there's sort of a convention here with the way that we draw these. So you can sort of think of y and z as, in some sense, being the screen right now. So the y and z sort of give us the coordinates for how we move around the screen. And, so this is going to be +1, this is going to be 2, 3, 4, 1, 2, 3, and then -1, -2, -3, so on. Okay. Then sort of coming out of the screen, but I can't really draw that, so I'm just going to draw it in perspective, is my x coordinates. And coming out of the screen is positive. So this is what my coordinate system looks like. And now let's say, do an example. And we want to plot 0, 1, -2. And we'll do 1, 4, 2. And again, to sort of make these stand out, I'll use a different set of colors for each. Okay. So for this first one, so I still read these, it's the XYZ plane, so I still read the coordinates. First coordinate is X. So I'm not moving out of the screen at all, not moving out here at all, I'm sticking here. My next coordinate is Y, so I'm at Y1, and then -2, so I move down 2. And that would be my point right there. For 1, 4, 2, I'm moving out 1 on the x-axis, so forward into the screen. I'm moving along the y direction 4. And if I sort of keep the perspective, note I will sort of stop before 4. And then I'm moving up 2. So that would be my point there. So we can plot points, but we can also plot sort of equations. We can plot in 2D space, right? We could plot y equals x, or even just a more simple line, like we could plot x equals 1. So let's get a sense of what does y equals 2 look like in 3-dimensional space. Okay, so we have this here, and I'm going to use sort of different colors just to distinguish this. But so this point, right, that I just sort of, I'll use green, I guess it stands out more. The point that I just marked there, that's going to be the point 0, 2, 0. Okay, not necessarily, super important to get that, but if I move out in the x direction, I'm also going to get a bunch of other points on this same plane. And same thing if I move up in the z direction. The one direction I'm not allowed to move is in the y direction. So I'm not allowed to move left or right. I'm only allowed to move up, down, or forward, back. But if I just sort of draw in some things like this, you can sort of get a sense of what it's probably going to look like. Oops. Try my best to draw that in perspective there. But what we get is a plane. So we don't have a line anymore, we have now a plane in R3. And there's other examples of planes you could get as well. So if we want to plot say y equals negative z, or z equals negative y. Okay, so we should know what the line y equals negative z or z equals negative y looks like, right? It's sort of this thing right here. Just lying in the yz plane. And then because I have no conditions on x here, right, I just sort of get a plane going like this. Yeah, something like this. So for these, you know, I'm not on an exam or anything, probably not going to make you try to draw something, but maybe at least identify something from a picture. If I do make you draw something, it'll be very, very sort of simple. Okay. So continuing, let's talk a little bit about how distance is going to work in 3D space. So first, just sort of a real basic example that if you think about, that makes a lot of sense. So what is the distance from x1, y1, 0 to x2, y2, 0? So these are points in 3D space, but because they have their last coordinate 0, hopefully you can sort of see that we can sort of treat them as points in the plane. And so we're going to get our answer it's going to be the same as if they were in the plane. And now here's the thing, it doesn't actually matter that these are 0. I could make both of them 1, both of them 2. As long as they are the same thing, they still sort of lie in a plane. And so we can just sort of use those coordinates. Okay. So more complicated example, let's look at a little bit more general case. So what is the distance? I'm not going to do arbitrary sort of coordinates just because it's going to be a little bit harder to draw, but from the origin which is the point consisting of all zeros, to the point x1, y1, z1. Okay. So here's how we want to think about this. So we have our axes. You know, we have some x1 coordinate, some y1 coordinate, some z coordinate. And what we're after is the length of this red line from here to there. So here's how we're actually going to figure out what this is. So what we're going to do first, give me some other color. I can't do black. Okay, I want to choose something different in case anyone's colorblind out there. I've never used this color before, but let's see. All right, yeah, this real funky, crazy looking line. Let's compute the length of that line first. Well, if I look at this crazy funky looking point, I haven't moved in the z direction at all. So the distance from the origin to this funky point is still going to be the square root of x1 squared plus y1 squared. Okay, and now what we're going to do is change our perspective. So now let's pretend, we have here, this is still our z thing, and let's assume we're just sort of looking dead on at the xy plane. So this whole sort of line here, the xy plane. I don't want to completely cover it up, but xy plane. Well, we have then this funky, crazy looking line up to our point, and then we have our distance again here. And we know what the distance of this is. It's that thing. And then the amount we're rising above the xy plane is just, well, the absolute value of z1. And looking at it, it should be pretty clear that this is also a right triangle. So I'm again going to have my distance formula. So distance equals the square root of funky crazy looking thing squared plus z1 squared. And the square root and the squares cancel, so I just get x1 squared plus y1 squared plus z1 squared. So now, that's sort of as complex as it gets. If I move from the origin to just another point, I'm just going to replace x1, y1, and z1 with differences, the relative differences. So distance formula in three-dimensional space. So the distance from this point to that point is the square root of x2 minus x1 or x1 minus x2, y2 minus y1, and z2 minus z1. Okay. So this is sort of our general distance formula between 2 points. Just take the differences, square them, add them up, and then take the square root. So now let's use this to figure out sort of, we know what circles look like, let's look at, circles in 3D, by which I mean spheres. So we want to find the formula for the sphere with center 2, 7, 0 and radius 6. And remember, if you think about a sphere, if you have the center, the sphere is just all those points which are some set distance away from the center. So for this case, we want all the points which are a distance of 6 away from 2, 7, 0. Okay. So I have my distance formula here. I can say x2, y2, and z2, that's just x, y, and z. And then my other point is 2, 7, 0. So that equals 6. And if I want to sort of write it in maybe a little bit more familiar form, I would square both sides, do a little bit of simplification, and get this. Okay, so it's really good to think of equations like this in terms of this distance formula. So what I want to do is I'm just going to sort of go through a couple examples, and I want you watching this video to maybe pause, take a minute, try to get some sense about why the things I'm saying are true. I'm not exactly the best drawer, so I'm not really going to try to attempt to draw most of these things, but yeah. So we're going to do a bunch of examples. So let's describe So I want you to sort of describe in words the following regions. And, you know, I'm going to eventually describe them in words, but really try to think about them for, 20 seconds or so, each one. So we'll start off with a real easy one. So x squared plus y squared plus z squared equals 25. So maybe take a minute, think about it. We see, okay, it's got to be a circle. Or I'm sorry, not a circle, a sphere with radius 5 centered at 0 or at the origin. Okay. So sort of continuing, let's look not at an equation, but a simple inequality. So think about what are all the points where z is greater than 0. And we can just sort of see that, okay, this is the top half of R3. So it's going to contain the point sort of on the XY plane, everything above that, but nothing below it. So this one, a little bit trickier maybe, kind of hard if you don't know like the words to come up with it. We have x squared plus y squared plus z squared is less than or equal to 9. And one thing to think about whenever you're doing problems like this, whenever you have an inequality, a really good sort of first step is to ask instead what happens at the equality. So x squared plus y squared plus z squared, if that equals 9, then we know that this is a sphere of radius 3. Centered at the origin. And so a way of thinking about this is this half is measuring the distance from the origin. We're less than or equal to 9, or really this is really the distance squared from the origin. We're less than or equal to 9, so what this tells us is that this has to be a closed, a filled-in sphere, which we actually have a special name for. We just call it a ball of radius 3. Okay, I'm just going to do 2 more slightly more complicated examples, and then that'll be the end of the video. Or wait, actually, I want to do one more example after these next 2, sort of on a slightly different topic. So again, we're, have these inequalities. We want to sort of figure out what shape it's going to look like. So we have 2 inequalities here. They're sort of combined into one expression. So let's look at them bit by bit. So first, we know 1 is less than this quantity here. And remember, we should think about this as distance squared from, in this case, we can look at the point 1 to -1. And so what this says is the distance squared from, we'll say this is our center, clearly there's some spheres involved. They have to be greater than a distance of 1 away. And similarly, if we look at the other part, Again, distance squared less than or equal to 5. So we can probably identify this using, we just sort of saw an example of this. Center's different. But this inequality by itself says it is a ball of radius 5 centered at 1, 2, -1. Another way of thinking about this first equation is it's not the ball of radius 1 centered at 1, 2, -1. So to sort of put those together, I can say the whole thing is a ball centered at 1, 2, -1 of radius 5 with center ball of radius 1 removed. I'm sorry, radius square root of 5, and that should be a square root up there as well. Okay, and the last example of these is going to be two separate inequalities. We'll have x squared plus y squared plus z squared is less than or equal to 1, and z is greater than or equal to 0. Okay. So again, this first inequality says it's actually the unit ball centered at the origin. So unit here just means it has radius 1. However, this second inequality says I'm only taking things which have a positive z value. So if I put those together and sort of think about what that's going to look like, then I'm going to get the top hemisphere of ball of radius 1 centered at the origin. All right. And to close off, I just want to give one more example. There's a couple problems like this on the homework. So x squared plus 2x plus y squared plus 6y plus z squared is less than or equal to -1 describes a I guess I'll make it equals. Nah, screw it. I'll make it less than or equal to. Describes a ball. So this describes a ball. What is its center and radius? So again, what we want to do here is just complete the square. So we take this 2, divide it by 2, and square it to get 1. So plus 1. And whatever I do to one side, I got to do to the other. 6 divided by 2 is 3. Squared that, I get 9. So then I add 9 to both sides. So I then have these two things, and so I have x plus 1 squared plus y plus 3 squared plus z squared is less than or equal to 9. And so I know my center is going to be -1, -3, 0, and my radius is going to be the square root of 9, which is 3. Right? And that'll end it for this video.